Hello, my name is John Long. I am a quantum software engineer at If and Only If Technologies, as well as the workshop director for quantum computing at Davis. I've been requested by Dr. Clarice Aiello to develop this lesson on behalf of her students taking her Quantum Mechanics for Engineers course to have this kind of introductory or introduction to Qiskit. And hopefully this lesson will cover about 80 to 90% of what students might expect to use on a daily basis if they're using a Qiskit for projects related to coursework. So I've developed this lesson around a singular Jupyter notebook that I'll provide a link to that you can, you're more than encouraged to use as future reference as you continue to get familiar with Qiskit and use it for bigger and better projects. So let me go ahead and screen share what that notebook looks like. So here is the notebook. It's hosted at this GitHub link here, github.com/iftech/UCLA Qiskit intro. IFTech being the organizational GitHub for If and Only If Technologies. Once again, this is for so this video is intended for Dr. Clarice Aiello's students, but of course, this is also it may have one or two specific examples, but for anyone out there who is not a student of this course, this should still prove to be what I certainly hope to be a fruitful resource in your journey of learning Qiskit. My objectives for this lesson are to show you how to build circuits, how to simulate them, and how to analyze the results. But I do want to emphasize, I have a second bullet point here about extracting the unitary matrix that represents a circuit and the state vectors that come from maybe starting in a certain qubit state and then seeing what comes out at the very end. And the reason for doing this is in all of my experience for being a quantum software engineer, it's incredibly helpful as you're developing your quantum circuits to be able to see what the unitary matrix looks like, as well as what the state vectors look like as a good sanity check. So as you're going along the way, you want to be able to sometimes pull the sort of underlying representation of your circuit into something like NumPy, where you can do a lot of what I would call like mathematical diagnoses, just to make sure that things come out properly, and you can do like matrix multiplication and multiplication with vectors outside of the Qiskit framework. And this will also help with your ability to transfer your skills to other quantum computing frameworks, because Qiskit isn't the only framework out there, although it certainly is one of the best by far. So that being said, why Qiskit? Why this quantum computing framework and not something like PennyLane or Circ from Google? Well, part of the motivation for teaching Qiskit is it's very beginner friendly, and it's thoroughly documented and very well maintained. There's no fear of this project ever being dropped or losing support anytime soon, and it's extremely broad. So what I mean by that is, if you decide, like maybe in the beginning of your quantum computing journey, to just focus on algorithms, but later on you want to transition to things like error correction research, or something like controlling individual qubits, so that's like hardware level simulations, Qiskit has it all. So you can, it's really nice that you can stay in this one massive ecosystem, and you'll be absolutely fine. But ultimately, though, my goal is not to make you accept Qiskit as the end-all word in the quantum computing space. And coming from an engineering background myself, the goal is to pick the right tool for the right job. And there's certainly no exception in quantum computing. You may find that as you develop more of these quantum circuits and more quantum algorithms, that one framework like Google Circ may be better tuned for what you want to pull off than what Qiskit can offer. Or maybe you're working with a specific quantum computer. So for example, Qiskit is generally associated more with IBM's suite of incredibly powerful and very well maintained superconducting silicon quantum computers, but you'll find PennyLane or Strawberry Fields is more tuned for continuous variable quantum computing. And if you have no clue what I'm talking about, don't worry, just know that you're in good hands using Qiskit for now. Now, I have split this notebook and therefore, by extension, this lesson into two halves. So the first half is going to be a lot of, I'm going to throw a lot of technical details at you, a lot of functions, classes, objects that you'll come across as you use Qiskit. And I'm going to structure this first half in terms of the number of qubits. So what I mean by that is I'll show you how to develop a quantum circuit with 1 qubit. Then I'm going to show you how to do it with 2 qubits, 3, and then you'll get up to what I call n qubit functionality. And the goal in doing this is that every time you get a bigger and bigger circuit, there are more and more things that you can do, more options and powers that Qiskit grants to you. And I think it certainly behooves you to be comfortable with these features, as they'll make your life much easier as you develop more complex and intricate algorithms. But the second half is hopefully the cherry on top, maybe a little more exciting. That's where I'll show you how to take what you've learned or what I've shown you and apply it towards sort of some real life algorithms. And you might be, there's Grover's algorithm, which I'm certain the vast majority of you already know. At least that's what Clarice has told me you guys know. And then there's also an example with the Givens rotation. If you don't know what that is, I'll give you a cool overview. And hopefully that example is, right now, it's not actually working perfectly, but my objective in showing you that Givens rotation is not so much that you know what it is, but that you kind of get a taste for what I mean by, it's really neat to see the unitary matrix and see the state vectors and the underlying mathematical representation of what you're working with, coming from my experience as a quantum software engineer. So let's jump straight into it. And we'll start with a simple circuit that only has a single qubit. So with any circuit in Qiskit, it's always going to be, you're always going to create this quantum circuit object. So you import it like so, from Qiskit, import quantum circuit. And there are two ways that you can create a quantum circuit. The first one is you call or you instantiate quantum circuit with a single integer argument, and this creates an empty circuit with 5 quantum registers. So I should be very clear here. A quantum register is really just a qubit. This terminology, you can think of them as equivalent things, a register and a qubit, but it becomes a little more important to make the distinction when we use the other form of instantiating or creating a circuit, which is when you pass in 2 integers. So the first integer here, this 3, means I want to create a circuit with 3 qubits, but then this other 1 here means that the circuit is going to have 1 classical register. So the objective in doing this is, in standard quantum computation, you'll perform, you apply your gates and all your unitary operations, and at the very end, we want to be able to use or get an answer out of the quantum state we're working with. And the problem is, you need a place to store the classical data, right? So after measurement, you'll get a 1 or a 0, but that 1 or 0 has to be stored somewhere. So that's where we declare these classical registers as kind of like little pockets of memory that you can store the results of your quantum computation in. So in this circuit, 3 qubits, and then I have 1 classical register. And later on, I'll show you how to link things so that your measurement from 1 qubit will get stored in 1 classical register. So yeah, for this part of the workshop, we're just going to stick with 1 single qubit and then 1 classical register. So a blank circuit isn't really that fun. So let's get to the second part, which is what you're probably itching to see done, and that's being able to add gates on top of the circuit. So in Qiskit, there are 2 main ways to add gates to your circuit. The first one is that usually your quantum circuit objects have built-in support for a wide variety of gates. I double-checked the Qiskit documentation for what's supported, but in general, all of your poly gates, controlled knots, Toffoli gates, they're all just built in. And what I mean by built in is you can just call this method, and usually the method name is going to be the name of the gate, but all in lowercase per, I think, all in lowercase. And then you'll pass in an argument, which is a number here. So, and that number is the index of the quantum register or qubit you want to apply the gate on. So in this case, we only have 1 qubit. So we use the number 0. So in Qiskit, the way you index your qubits is there's 0 indexed. So your first qubit is going to be accessed by the number 0. Your second qubit is going to be accessed by the number 1, so on and so forth. The other way, which is a lot more explicit and which might seem redundant now, but you'll soon find why it's so useful, is you can explicitly add a qubit that add a gate that you might have declared externally with the .append method. So you see here that I've imported the X gate from this circuit library that Qiskit offers. And then what I'm saying here is like, look, I want you to append the gate to the circuit, and I want this gate to be applied to the 0th qubit. The qubit with index 0, which is really our first qubit. And so once again, right now this seems very redundant, but I assure you that as I show you how to build your own gates and even turn entire circuits into their own kind of gates, QC.append becomes incredibly useful. Now, although it's, so now we know how to add gates to our circuit, but it's always nice to be able to see what our circuit looks like, right? It is a circuit after all. And, one of the things that goes hand in hand with circuits in both the quantum computing sense and more traditionally in the electrical engineering sense is we have some kind of schematic, some visual way of seeing our circuit. And Qiskit does a fantastic job of offering native support for visualizing what your circuits look like. You just take the quantum circuit you're working with and you invoke the draw method. And what draw does is literally just generates this very nice diagram for you of your circuit. And you'll notice here that each of our gates is represented by some nice square with the letter inside the square representing the gate in question. And then at the bottom here, you'll see there's a C with a 1. So what this means is that we have one classical register, C for classical. And right now, one of the things I want to mention is that if you are like me and you use the command line a lot for just sort of quick and dirty testing, this rendering here will come up identical on the terminal. So this is all, I imagine it's probably some ASCII level stuff, but it comes out very cleanly even on the terminal, which is fantastic if you just want something quick and dirty. But most of the time when you're working in a Jupyter notebook, you want something a little shinier, as I like to say, or perhaps you want to even save your figures for maybe an assignment or a research paper you're working on, in which case you can pass in an argument called MPL. MPL is short for mat.lib, so output equals MPL. And voila, we get this like really pretty a much prettier representation here, still the same symbols, but it just looks a lot nicer. So awesome, we've built our first qubit. Now, before I show you how to simulate it, let's perform sanity checks. The way I like to think of what I would think of as a sanity check, it's a sort of a very quick test to sort of isolate a certain part of your program or circuit and really verify that it's working the way you think it works. It's kind of it's operating in a sane fashion, this goes all the way back to good software development practice, right? When you are trying to isolate a bug, you want to make sure that all the things that you think are working are working. And like a good experiment, when you are developing an experiment, you have one very well isolated independent variable and one dependent variable, and you want to eliminate all of what we call these confounding factors, so things that are out of your control but that may still affect the dependent variable. So just being able to test things one at a time at a sort of a more fundamental level. And we know that before, in this case for our circuit, we know that applying two Pauli operators, the same Pauli operators I mentioned. So in this case, we have two X gates back to back should return the qubit to its original state, which means that the unitary matrix that represents our circuit should look like the identity. So we already know ahead of time, like in our heads, we expect the identity. And as part of the sanity check, let's make sure that it actually is the identity matrix. So the way you can convert your quantum circuit into this unitary matrix is basically just 3 lines of code here. From qiskit.quantuminfo, we're going to import this operator, and then we just pass in this operator class, and then you just pass in the quantum circuit as an argument when you're instantiating this operator. And this gives you the ability to, once you use the .data attribute, you can access this NumPy. This is a NumPy array. You can visually confirm this is the identity matrix, which is perfect for what we want to do. And kudos to Christopher J. Wood. He is the lead Qiskit Air developer. And Qiskit Air, by the way, is the framework in which you will use to simulate your circuits, both either on the simulator or on a real quantum computer, a real IBM quantum computer. And yeah, I got this answer off of the Quantum Computing Stack Exchange, which is another fantastic resource you should check out yourself. So besides getting the unitary matrix, we may also want to see what happens to a qubit initialized to Ket0 when it goes through the unitary, or more correctly, when we apply the unitary by a matrix multiplication. So we can import this state vector utility. And what happens is when you state vector automatically assumes that you're starting with Ket0, so you can do state vector dot from instruction, and you pass in your quantum circuit here, and it will give you your new state vector. And in this case, the state vector is still Ket0, which makes sense because our unitary matrix is the identity, so nothing should happen at all to our quantum state. Now, something I want to clarify is, like, why is this method named from instruction. And it's because if you really dig deep, you'll find that the representation for quantum circuits is really it can be interpreted as a sequence of these instruction objects in Qiskit. So that's why from instruction literally means like, well, your quantum circuit is a list of instructions. So from these instructions, generate my state vector. And that's what we've done here. So this is, fun and all, but it's kind of boring. I've only shown you the identity. So let's spice things up a bit, and we'll throw in the Hadamard gate. So we're going to create a new circuit. Once again, we only want one quantum register and one classical register. We are applying the Hadamard to our first qubit, which is indexed by 0. And then we're going to take advantage of matplotlib to create this very shiny and pretty diagram or schematic for us of what our circuit looks like. And let's use what we've learned. Let's see what the unitary is. So once again, we're going to pass in the quantum circuit to the operator here, and then extract the data using the data attribute. And this gives us a NumPy array. And right now, I know this does not look like 1 over the square root of 2 with a matrix of 1, 1, 1, -1. But if you look at the signs here, right, you can imagine that there is a 1 over the square root of 2 coefficient that's been applied. And if we look, they're all the same value, except for the last one, which is negative. So that confirms it's 1, 1, 1. -1, although it may not look like it. And let's see what happens if we send in a qubit with the ket 0 as our initial state. So we're still using the state vector tool here, and then we do from instruction, passing in our quantum circuit, and we see that the state vector is still is ket plus. So this is essentially this quantum state here. And it's if you remember, this is equal to ket 0 plus ket 1 over the square root of 2, which means you've got a 50-50 chance of falling into 0 or 1, and this seems to make sense. So we've done like a mathematical sanity check. Now that we know how to get the unitary matrix and the state vector out, it's also nice to be able to visualize your quantum state, because I know a lot of us when we learned initially quantum computing, one of the great ways to learn what all these unitary operations and gates do is our old friend the block sphere here. And Qiskit has a built-in function for visualizing the block sphere. It's this function called plot block _ multivector. And all you have to do is pass in the state vector. So here's the state vector up here. You pass in the state vector as a result of having applied your circuit, and it will show you the block sphere automatically. And we can tell that we're in the ket plus state. So that's ket 0 plus ket 1 over the square root of 2. And you might be wondering, this naming convention, right? Why do we call it multivector when I've only passed in one vector and it only seems to display one vector? Well, there are sort of two reasons for this. The first one is that Qiskit does have a plot _ block _ vector function, so no multi, just vector. But the problem with this function is that it requires you as the user to manually convert your state vector into a Cartesian or polar coordinates, which is not really what you want to deal with when you just want to see what the quantum state is. That's one reason why I guess they had to use a different name. The other reason, though, and the more intuitive understanding, is that the multi and multivector actually means like and I'll show you guys what happens here. If you have a circuit with more than one qubit that is not entangled, and emphasis on not entangled, Qiskit will be smart enough to actually separate that one big state vector into multiple state vectors, and then it can show you the block spheres for each qubit. So, and it does it automatically. You don't even have to explicitly tell Qiskit this many qubits. Qiskit will automatically infer that from how big the state vector is and give you these multiple block spheres. But there is another visualization that is also really nice to have. And this will probably be more useful to you as you learn more about quantum computing and you learn about the density matrix formulation of quantum mechanics. And the density matrix is not something that's inherent to quantum computing. This is from quantum mechanics. And the idea is you may encounter scenarios where you don't have all the knowledge of the quantum state, in which case you have to express it as, and I'm quoting this from the Nielsen and Chuang textbook, which I strongly encourage you to take a look at yourself. I think it's at the end of chapter 2, is where they give this very nice definition of the density matrix. And it's where you are represented as an ensemble of quantum states versus what we're more familiar with in the state vector representation, which is this, it's a sum of these probability amplitudes applied towards basis states. So yeah, in the case where you may not be able to, you may have what we call like a mixed state. So you're uncertain of what the actual quantum state is, and you just know it's a mixture of other quantum states. And basically the way you generate a density matrix is really you take your state and you just take the ket and then times the bra, so that you take the outer product of your quantum state against itself. And in this case, you can see the real and by the way, this operation here, this outer product is going to generate a matrix. So remember that the inner product will always give you a singular imaginary number, but for the outer product, you get a whole matrix that can be full of imaginary numbers. And that matrix can be thought of as a density matrix, although the other formulation is a summation against the outer products with respect to the basis states. I'll once again, I encourage you to look at the Nielsen and Chuang quantum computing textbook, where they give a much more rigorous definition here. But I just want to get you guys to know that density matrix is another way of looking at things, and certainly there's also a nice way that Qiskit offers that you can visualize it with, and it's this state city plot. And what's going on here is it's showing you the real and imaginary numbers, because once again, this matrix from the outer product can have complex value entries, and as a result, you can visualize just the real components and the imaginary components. And you'll find that if you take ket plus and then you outer product it with itself, you're going to get a matrix that has 0.5 for all its entries. So that's why here we see we have 0.5 for all the real components, and there's no imaginary component. Something to keep in mind though is like what is going on with these the 0 and 1 here is you can think of these as ket 0 and ket 1. And what happens is if you take the outer product of ket 0, and then plus maybe ket 0 with this is ket 0, bra 0, ket 0, bra 1, bra 1, and then you just kind of alternate through all of the bits here, single bits, so 0 and 1. You'll find that you actually generate a whole matrix with ones in its entry. So each one of these will generate a matrix with all zeros and then just a single one somewhere in it. And then you can associate a coefficient, or some coefficient here, and this would also be an equivalent representation of it's sort of like a broken down version of what I showed you earlier, which is you just take your quantum state ket psi and then ket psi here. So basically what's going on here with like the 0 1 0 1 is you can imagine this ket 0 ket 1 outer producted with the outer product applied to say another ket 1 or another ket 0, and then the sum of these with individual coefficients can give you density matrix. I'm just trying to rationalize the notation here. So let's now that you know this. Oh, and by the way, this state city visualization comes in real handy, because when you have an entangled state, you won't be able to use or rely on the block sphere. So you want to get comfortable with being able to understand what's going on with the density matrix and the state city plots, which always work regardless of what your quantum state is, if it's pure or mixed. So let's now that we know these visualizations, unitary and state vectors, let's go ahead and actually run our circuit. So in the real world quantum computation, I kind of alluded to this in the beginning. The only way to get useful information that we can use out of the quantum algorithm is perform a measurement at the very end, which will collapse our quantum state into some classical state. And we need to be able to not only perform the measurement, but save that data somewhere. So in Qiskit, the way you would do this is we invoke measure here. And what this is saying is like, look, apply a measurement on qubit 0, and then save the result of that measurement to classical register 0. So the classical registers are also indexed by 0. And once again, I'll draw just to show you what the circuit looks like. And lo and behold, we now notice this additional black square with this kind of a meter-looking symbol, and then an arrow pointing down. So it means like, look, I'll apply the measurement, and then this data is going to get chucked into the classical register. Now you have two options once you've applied your measurement operation. Is you can run it on an actual quantum computer. So that means you need the credentials for an IBM Q account, which will allow you to submit your circuit as a job to real-life quantum hardware. Or most of the time, you can just run it on a simulator, which is what we'll do here. And what you'll probably be doing the majority of time is because even with an IBM Q account, you will be forced to wait in line against all the other jobs that are waiting for access on a quantum computer. And that can take anywhere from 5 to 10 minutes, if you're lucky, to maybe a number of hours even, depending on just how busy that one machine is. So what we'll do here is, I mentioned earlier that Qiskit Air is kind of this, is a part of Qiskit that's responsible for letting you simulate circuits as well as run them on real life hardware. So in this case, I'll import this Air simulator class. And there's a wide variety of simulators that you can select. I certainly encourage you to check out the documentation that I've linked here, because you can select the way the simulator behaves by passing in this string here as part of the instantiation. So for the majority of purposes, the state vector simulator will do just fine. And part of the simulation process is, once you define a backend, that's what they always call it. So the simulator has now been assigned this variable called backend. You're going to want to invoke this run method with, and you pass in your quantum circuit to this method. And you'll notice here, there's another argument that I've passed in called shots, and I set it equal to 1024. So in Qiskit, when you run a circuit on a simulator or real hardware, when you run it once, it's called a single shot. So in this case, I'm telling Qiskit, I want you to simulate the circuit 1,024 times. So 1,024 iterations of the same circuit. And then every time you run a circuit on a backend, you'll get what's called a job. And then from that job, you can access the results. A job doesn't really make much sense locally because we're simulating things, but it makes way more sense when you submit to a real life quantum computer. So you've essentially, you can think of it as your quantum circuit along with the additional metadata for how to run your circuit is encapsulated in this job object. And that job object will get passed to the real life quantum computer. You can monitor the status of your job, and then you'll be able to access the result from that job. But so this is if you were running this on a real quantum computer, but in this case, we're just running it on the simulator, but the terminology stays the same. It just, in my mind, and hopefully in yours, it makes more sense why we would call it a job. So, once we run the simulation, you can extract your results from the job, and then we can look at the counts. So the counts here being like how many times did our measurement return 0 and how many times did our measurement return 1? And this is just for our single qubit circuit. If we were running a circuit with multiple qubits, then you have multiple possible, more than just 0 and 1 as potential measurement results. But in this case, so we see that we've measured 0 514 times, and we've measured 1 510 times. This is about 50-50. And this certainly makes sense to us because we applied the Hadamard, and the Hadamard always gets us into an equal superposition if you start out in the initial computational basis, so you start in Ket 0 or Ket 1. Now, you might be wondering, 1024 is perfectly divisible by 2. So why is it the case that it turns out that we have unequal measurement results? It's a simulator after all. Isn't the simulator supposed to be perfect? And you're right. And it turns out that the state vector simulator still tries to add sort of a minor degree of randomness. I believe you can actually seed that randomness or configure it. And by seeding, I mean like you can pass in some constant, which will allow you to replicate the randomness you encountered. Because it's with random number generation, usually it's a pseudo-random number generator. So if you pass in the seed, you can get replicatable results, which is fantastic if you're comparing or if you're sharing your work with someone else, or just you want to show off your research here. There is, I think, the unitary simulator. So if you were to pass in method equals unitary, I don't think it introduces a randomness component, although the caveat with using the unitary simulator is you can't perform the measurements. And that makes sense, right? Because a measurement is not a unitary operation. In fact, it's probably one of the only permissible non-unitary operations in quantum computation. But I digress. Now that we have these counts, Qiskit also can allow you to just plot a histogram of your counts. And you'll probably do this very frequently for your other projects. And notice that inside the visualization module of Qiskit, and very aptly named because that's where all of the visualization tools I've showed you are stored. You can import this function, plot histogram, and then just do result.getCounts, and it shows you a very nice histogram of your the number of counts. One of the other things that you can do, which is also kind of neat, is another feature that I want you to be aware of, in fact, is that you can save the state, you can save your quantum state after running it through the simulator. So if you add this method here, save_state, that allows you to save the state vector after running the experiment, and you can view it later. So in this case, if I go ahead and run the same circuit again and get the state vector, we'll notice that it's ket1 because it's ket1. And right now it's not really interesting because you'll notice that if I were to go back, I call save state right after we perform the measurement. So at this case, we've already kind of collapsed the quantum state into a classical state. So there's nothing really exciting going on here with using save state. But where save state really shines is that you can place save state at an intermediate point in your circuit. So I'll do quantum circuit 1, then I do the Hadamard again. 1 being 1 qubit and then 1 classical register. Apply the Hadamard to that qubit. Then I apply the save state right after the Hadamard, and then I add the measurement operation after the save state here. And you'll notice that in this case, like now I can actually see the intermediate state of my quantum circuit. Now I'm fairly certain save state doesn't work for if you're running this on actual hardware. I don't think you can save the state there, but for simulation you certainly can, and you can arbitrarily inject save state anywhere, and then after your simulation, you can, from the result of your job, you can just call get state vector, and it'll get you this this saved state vector. Now, even though we ran the circuit 1,024 times, I think it'll only give you like 1 state vector, and I'm fairly certain that this is the state vector at the very end of all these shots. But if that isn't the case, it's at least one of the shots, I imagine. So yeah, you can save your intermediate state vector. Now, for all of the operations I've shown you, all these simulations and using the state vector tool that you imported, they all assume that you're initialized in ket0. But what if we want to start in some other initial state, like maybe ket1 or ket0 plus ket1 over the square root of 2, or which in this case is still a ket plus, and Qiskit lets us do that with ease. So for a basis state like ket1 or a ket0, we can just declare our quantum circuit as usual, and then you can use this initialize method here, where you would pass in this case, you can pass in a binary string. So it's a string of 0s and 1s, and that should indicate an initial state for your quantum circuit. And then if I draw it, you see we have a purple square here with the ket psi, and this should indicate like, okay, so the circuit at the very beginning will start in the ket1 state, or the 1 state versus the standard 0. And just to be safe, we can check that this is the case. So I'm going to pass the quantum circuit into the state vector here, this method into the state vector tool here, using this method from instruction. And then we see it's 0 in the first entry, 1 in the second entry. So indeed, we are in ket1. So this is a good method to sanity check that what you are applying to your circuit is actually what's going on here. But for something that's not a 0 or a 1, maybe some kind of superposition, you can do the following. So in this case, I need the square root function from NumPy just to help me kind of wrangle the initial values here. But the idea here is you still declare a quantum circuit as usual. But then in initialize here, we pass in a list, and this list represents the state vector that I want the qubit to be in. So in this case, it's 1j. The j here in Python is the way of expressing an imaginary number. So it's technically I over the square root of 2, and then 1 over the square root of 2. And then if I do qc.draw again, and then we can see we still get the purple kind of square here, but at the bottom you can even see the initialization values of 0.707j and then comma 0.707. So that's what I over the square root of 2, and then the square root of 2 by itself. And just to sanity check again, we can do we can pass in this quantum circuit into the state vector tool, and then see that we've actually the circuit is actually in this state from the get-go. So on top of being able to provide a custom state to initialize your qubits in, there's also the option of being able to develop your own custom gates. And this might be particularly useful if you encounter a gate in maybe research or something you've come up with yourself that isn't natively implemented by Qiskit. And it's certainly something that I imagine will be advantageous as you continue to build projects. I kind of alluded to this functionality in the very beginning when I showed that there were 2 methods to implement gates in Qiskit. So hopefully this will kind of continue off that vein. So one of the main method of doing this is to use this guy here, a unitary gate. You want to make a unitary gate object. So the first thing you want to do is create the matrix that represents your gate. I've gone ahead and done this by taking advantage of NumPy's offering here with np.I, which is just a way to create the identity matrix. And then I pass in the number 2, so it's just 2 by 2 identity matrix. And then I'm going to create a quantum circuit with just one qubit. And then I'm going to go ahead and pass in the matrix representing my custom gate here, along with a label that goes with it. And the label is what's going to get displayed if I print the circuit here. So then I use append now, which is our kind of our explicit method of adding gates to circuits. And then I pass in this unitary gate object with the number or the index indicating which qubit I want to apply the gate to. And then we just do a dot draw, and then we output via matplotlib on the circuit, so we can see what the actual gate looks like here, and it comes up very nicely. Now, something that Clarice explicitly wanted me to cover for you guys is the idea of rotation gates. So we know that for the poly matrices, the X, Y, and Z poly gates, they make a rotation of pi radians around the Bloch sphere of each respective axis. But there are many scenarios where you will want to do some fractional degree of rotation. So instead of pi, maybe you want pi over 3, pi over 8. And yeah, for like a concrete argument as to why you would want these fractional rotations, the best example I could give you is VQE, the variational quantum eigensolver, where you are literally modifying a quantum state to try and get the lowest possible eigenvalue and the associated eigenstate with it. And it's almost like if you were maybe cracking a safe, right? And you can imagine that, well, if you're restricted to turning the dial on that safe to like only 90 degrees every time, or 180 degrees, you wouldn't be able to crack the safe. So you need to be able to access the entire all the rotations possible, and having these rotation gates will allow you to do that. Mathematically, they're just kind of like they just look like a parametrized matrix, and it's something that you can check on the documentation yourself. But they accept a singular argument, usually a singular argument that will then define to what extent you're doing the rotation. I think it's the matrix put as the exponent e to the I x theta, or e to the I y theta, or e to the I z theta. Usually it's I think it's theta over 2 in those. Part of the example here, I'm going to declare a quantum circuit with a single qubit. Then I import NumPy, and I'm only importing NumPy because I need to access the constant pi. If you don't have access to NumPy, you can use, I think you can use Python's built-in math library. Yeah, so basically .rx, so rotation about the x-axis of pi over 3 degrees. And then you see I put in 0 here to indicate that this gate should target this singular qubit, or qubit 0. And then we go ahead and draw it to see what the circuit looks like. And we can also extract the state vector, once again, using the state vector tool here. And then we pass in our circuit into the from instruction method. And then we use plot block multivector, and then we can visualize it here. Now, it might initially confuse you as to why, like, well, you said pi over 3, so that this doesn't really look like a third. Well, if you recall the domain of the Bloch sphere, so you remember the Bloch sphere is defined off the top of my head as cosine theta over 2 ket 0 plus e to the phi I times sine theta over 2 ket 1. So basically you don't actually, your vector doesn't actually, like, the domain doesn't wrap around the entire, it's cut in half essentially. So that's why it seems a little, this degree of rotation seems smaller than you may initially want to, intuitively may think it to be. And you know, plot block multivector, super useful function here, and it just automatically generates the sphere for us. And likewise for, you know, not just for Rx, we also have Ry for the Y gate. So this is rotation about the Y axis. And we also have Rz. So that's rotation about the Z axis. And you could tell, well, you know, nothing happens because if you're already in the Z gate, it just adds this kind of global phase. And it's nothing you can really visualize. If you wanted to see something on Z, you could apply maybe Rx or Ry to get it off the vertical axis. And then you'd be able to see a rotation about the Z axis. But you know, these circuits, you know, Rx, Ry, and Rz come up all the time in VQE, and you may find them useful for your own objectives. So to recap, now you know how to create an empty circuit, how to add gates to a circuit, how to obtain the raw state vector and unitary matrix representing a circuit, how to simulate a circuit, and how to visualize circuit results and qubit states. So, but this is all for a single qubit. Now what I want to do is kind of increase the complexity here and start messing around with 2 qubit circuits. So this is where we get to the 2 qubit stuff, as I like to call it. So yeah, let's extend what we know. So we can, just as easily as we created a single qubit circuit, we can create a 2 qubit circuit. So in this case, I just pass in the number 2, meaning I want 2 quantum registers, and then another 2 to represent 2 classical registers to store the results of measurement of my 2 main qubits. The single qubit gates can still be applied as usual. So in this case, I have a Z gate that's targeting the first qubit. Once again, recall that our qubits are indexed 0 index. So the first qubit's indexed by 0, the second qubit is indexed by 1. So we have, and then you see for the X gate, I can put it on the second qubit by just punching in the number 1 here. And we also have the ability to apply 2 qubit gates now. So in this case, the general pattern is that the first integer you pass in for the majority of them, the intuition is that the first number you punch in, or the first few numbers will be for the control qubits, and then the last numbers may be for the target qubit. So in this case, our control qubit is qubit 0, or our first qubit, and then the target qubit is qubit 1, or our second qubit. And then we can go ahead and visualize that. And in this case, you see I've applied this CX gate after our Z and X qubits, or Z and X gates on the first and second qubits respectively. And we can still use the same state vector tool, passing in the quantum circuit to from instruction, and you can still see the state vector here, along with being able to, and this is where plot block multivector really shines, is being able to visualize the state of multiple qubits automatically. So there's no need for you to explicitly tell Qiskit, hey, you know, this circuit has n number of qubits. Qiskit will figure it out for itself. And you know, once again, the state is separable, and I want to emphasize that. So if you have, you know, in the beginning when you learned about the difference between entangled and non-entangled states, we know that the state vector for non-entangled states is reversible. So if it's the tensor product of two smaller vectors, then you can go back from this larger tensor product vector, and then you can go back to the individual vectors. Whereas for an entangled state, you cannot reverse that operation. So you can't, or to be more specific, you can't separate that original vector back into two other smaller vectors. So in the case that it is separable, Qiskit's very happy with this thing here. Oh, and another word of caution going forward is that Qiskit has the qubit ordering flipped. So for example, I'm citing this from the one of the tutorials here. So for example, if qubit 0 is in state 0, qubit 1 is in state 0, and qubit 2 is in state 1, Qiskit will represent the state as 0, 0, 1. So in this case, we'll go ahead and you know, you can still so yeah, the qubit ordering in Qiskit may be flipped from what you're originally familiar for, and I forget what the exact argument Qiskit has for doing this, although sometimes it can be somewhat annoying. And then we have, so state city also auto scales, just like plot block multivector. So you can put in your state vector, and you can still get this very nice state, what they call a state city plot, which is once again the density matrix of our state. And you can see it's all clustered around ket 1, 0. So this would be the equivalent of saying something like this here, ket 1, 0, and then 1, 0. So it'd be the outer product between these two states. So these are, you know, this is a pure quantum state, but you'll definitely see some more interesting stuff as you deal with what we call like mixed states. And once again, you can still obtain the unitary operator by passing in the quantum circuit to the operator here, and then you can extract the data like so, and this would you know, this matrix represents the unitary matrix for the entire circuit. And the syntax for running simulations stays pretty much the same, but something that I do want to mention is that, you know, you want to add a measurement as the last operators of the circuit. So for multiple measurements, you can use the measure all method, which is kind of like it's a bit of a shortcut. And what it'll automatically do is it's going to create the measurement gates for each individual qubit, and then it's going to also automatically create a classical register to go to. So even if you declared the circuit originally without classical registers, using measure all will add those classical registers and then automatically link the measurement operations to the classical registers. But if you have initialized the circuit with classical registers already and you want the measurements to go to the existing classical registers, then you want to use measure underscore all with the argument add bits equals false, because otherwise measure all is going to assume like, oh, there's no classical registers, and it creates a separate pair of classical registers, which may not be what you want to do. So that being said, if we go ahead and do a nice qc.draw here, we would find that you have your your circuit here all nice and set up. And once again, we're going to create an error simulator using the state vector simulator. We're going to run it 1,024 times, get the result from the job, and then we can look at the counts here, and we see that the circuit's designed to only be in one state here. So naturally, it's set up like this. And once again, I want to mention, so if we go back up here, you notice qubit 0 is ket 0, and then qubit 1 is ket 1. But if we look at the way this is written, it says 1 0. So this is just a friendly reminder that Qiskit does flip the ordering of the qubits. And you can certainly still save the intermediate state vector as well. So you remember in the single qubit circuit, one of the things that I did was I mentioned there's the ability to input this kind of instruction here into your quantum circuit. So during the simulation, it'll say like, hey, let's save what the state vector is either prior to performing the measurement or after performing it. Although if you save the state vector after measurement, it's not really that useful because it's going to be the same thing as what the measurement provides because you've already collapsed the quantum state. But yeah, you can still use save state vector. And this time around, you see the syntax remains exactly the same, and you'll get your final state vector. And then once again, you just same thing, right? You just run the circuit 1,024 times, and then you can extract the result from the job, and then you use the get underscore state vector method on the result to get the actual state vector here. Now, with 2 qubits, we know we can still do custom initialization, and this certainly is true for any number of qubits. But now that you have multiple qubits, you kind of have some more flexibility with what you can do here. So, for example, maybe I only want to initialize 1 qubit to a certain state, and I want to leave the other qubit in ket 0. In that case, you can still provide a list here, a Python list that gives the state for that 1 qubit, but you have to add this other integer here, and this other integer tells Qiskit like, hey, this custom state applies to that particular qubit. In this case, it's ket 0, and you're passing this into the initialize function, and we can see it still works here. But you can also, for more complex setups where maybe you want the entire, so all the qubits have the same, are part of this initialized state, then you can pass in an even larger list. So in this case, I've created an entangled state here as the pre-initialized state, and I don't have to pass in the integer anymore. Although generally, from what I've seen, Qiskit prefers that, or at least the Qiskit documentation always prefers to put in the number of qubits, even though it's not really necessary, just to be explicit, to make your code maybe a little more readable. But ultimately, I leave that up to you. And then you see, like, look, now we have both the qubits as part of this initialization component, and they're all being targeted. And further, if you have initializations where you just want to pick between starting with 0 or 1, you can certainly just pass in a binary string. So just literally a string of 1s and 0s versus, it wouldn't work if you passed in just 1 and 0 because that gets interpreted as 10, and then Qiskit will try and translate that 10 into binary, which doesn't really work out because you only have 2 qubits, right? So the highest you can go is 1, 1, or the number 3. So yeah, and then it'll work out here, and then keeping in mind the flipping of the ordering here. So yeah, if we look at the state vector here, it comes out just fine. The reason I keep, once again, the reason I keep putting in from instruction and state vector is to kind of drill it into your head. Like, this is a fantastic way to just make sure that things are working the way you expect them to work. You can also just pass in an integer. So in this case, I think I just put in the number 3 here. I don't know why I said set qubit 0 to. I think this is because I accidentally copied it over from another another cell that I had earlier, so ignore that comment here. But basically, if I do QC.initialize 3, then the entire quantum circuit is now initialized into the 1-1 state, right? Because in binary, 0, 0, and then all the way to 1, 1. The 1, 1 is the number 3 in binary. So you can pass in an integer, and Qiskit is smart enough to auto-translate that to a larger state here. You can still define custom gates here, but with more qubits, as I like to say, comes more fun. One of those additional components of fun here is that you could define custom controlled gates now. So you remember like the controlled X gate or the CX gate or the C0 gate. It has like 3 names. You have a controlled qubit and a target qubit, and basically once the control qubit is in the Ket1 state, then it's going to apply the gate to the target, otherwise nothing happens. So in this case, let's first create our quantum circuit. In this case, I'm creating one with 2 qubits. We're going to create a custom gate. So notice this is still a 2x2 matrix. And intuitively, this doesn't make sense because if we have a circuit with 2 qubits, we need a 4x4 matrix to actually represent an operation on that. But luckily, Qiskit makes creating these controlled gates really easy. In fact, you don't have to rack your brains over what the matrix should look like for the controlled gate. You just need to know what your target gate is. So in this case, it's just the identity. And you see I've given it the label identity. And then what happens is you can invoke this method here, dot control. So after you've created your custom gate, which is a unitary gate instance, that has a method called dot control. And in dot control, you can specify, look, I want the number of controlled qubits to be 1, and I want this controlled gate to be labeled controlled identity, or whatever you want to name your gate. And then you can go ahead and add the gate, and then you see that we still have a list here. So we're using qc.append, and then we put in the unitary gate, and then, but this time because it's a 2-qubit gate, we need to specify 2 integers. The first number here would be the control qubit, and then the second number here would be the target qubit. And if we go ahead and do qc.draw, you can see we get this very nice automatically generated controlled qubit. And once again, the default behavior is that if the controlled qubit is a Ket1, we go ahead and apply our custom gate, and if it's anything else, nothing happens. But what if we want the control gate to only trigger when we detect a 0 instead of a 1? So traditionally, what you would do is maybe you put an X gate in front of the control here, just to kind of get that behavior. And maybe you'd undo it too by putting another X gate afterwards. So you're not like, you're not making a permanent change in the rest of your algorithm. But Qiskit makes this even easier because with the same code from here, where we're adding our control gate, we just tell it, hey, the control state, the control qubits should just be in the state 0. And we can still preserve the label and everything. And now if we draw it, notice that this first one was the first time I showed you, but this new gate, the circle here on the controlled qubit is now white, which is your indicator that this only triggers on Ket0 instead of Ket1. And hopefully you can kind of already get a hint here that if I can explicitly define the number of controlled qubits and the control state, then this will certainly be even more powerful as we get on to 3-qubit circuits and n-qubit circuits. Now, I want to give a quick word on visualizing entangled states. I know I kind of already talked about it with the plot block underscore multivector function, but I think it's worth definitely emphasizing it here one last time. So when an entangled state is created, by definition, it's non-separable. So you cannot split the vector that constitutes it into 2 separate vectors. So this does kind of put a wrench into visualization, but only partly. So I'm going to create this circuit here. And this should be very familiar to you all. This is how you generate a one of the 4 Bell states here. It's a quantum circuit with 2 qubits. We apply a Hadamard on the first qubit, and then a CX gate with the first qubit being the control and the second qubit being the target. And then we go ahead and just draw it here. And we can get the state vector for this resulting circuit. So remember, state vector always starts with Ket0. And then when you apply dot from instruction, it implies like the instructions that constitute your quantum circuit to that initial Ket0, and it gets you the new state vector. And if you try and visualize it, well, you're in for a pretty disappointing result because there's literally nothing here. And so, behold, you don't get anything. And this is generally the case whenever you run into entanglement. Qiskit just fails to properly display separate block spheres because it's impossible. I mean, you can't separate the quantum states here. And sometimes you can still get something, but what I've noticed from my personal experience is that something is usually your vector is dwarfed. So it's instead of like touching the surface of your block sphere, it's like retracted in, or it's like outside the block sphere. So now the arrow is like touching the outside of this. It's like not even on the surface anymore. It's like above the surface, which is really weird. It just makes no sense whatsoever. But the density matrix formulation is where this shines. And in fact, this is another way to kind of circumvent what the block sphere can't display. And you can certainly still see the sort of city-state diagram here. And it'll still hold up. So this might be another, so the density matrix formulation is certainly something I would encourage you to get familiar with. And then once again, you see like the 0 zeros and the 1 1s here. So these are kind of your basis states. And you remember, you can kind of index each entry of the density matrix, or rather that component, because if I do something like ket 0 0, and then I outer product it with 0 0, like so, you're going to get a 4x4 matrix, and you're going to have a that's all zeros except for 1 in the upper left corner, if I'm not mistaken. And then if I change this to maybe ket 0 1 and then ket 1 0, you'll notice that you can create like this kind of summation going on. And then for each one of these, because it's almost like overlapping matrices, you can put a coefficient in front, and it will, and that coefficient can be, in this case, it'd be 0.5 for maybe ket 1 1 outer producted with ket 0 0. But more intuitively though, besides this kind of minutia, you're just taking your current quantum state and then outer producting it with itself. And that's how you could get the raw matrix if you wanted to. Now, you might be wondering, is there a way before I have to plot things to tell, like, maybe my system is partially entangled or fully entangled? And there's a really nice or fantastic answer here from the quantum mechanic user on Stack Overflow, or more importantly, the quantum computing stack exchange. And the idea is to use an operation called partial trace. So the one of the shining points, and this is something that Nielsen and Trong also mentions, for using the density matrix, is when you have an ensemble or like a multi-qubit system, and you only want to get the information on, say, 1 qubit out of this multi-qubit system, then one of the things you'll have to do is apply the partial trace. And there's a way to apply it in such a way that you can determine is the system entangled, or if it isn't, in which case then it'll be safe to maybe visualize with the block spheres. Otherwise, you're going to have to resort to the state city representation here. So now, we've covered 2 qubits. Now we can kind of go to n qubits here. And there are a couple of other neat things that you can do as you get to kind of larger and larger circuits. So in terms of building circuits, still, you initialize a quantum circuit the exact same way. We go ahead and you pass the number 5 to represent that you want 5 quantum registers along with 5 classical registers. And then you can still apply your single qubit gates. See, I have like an RZ, a custom, an explicitly defined rotation around the z-axis. In this case, it's pi over 8 being applied to qubit 1. And then there's the z gate being applied to qubit 0, the y gate being applied to qubit 3, the x gate being applied to qubit 2. And we can also apply, like now you can see we have like 3 qubit gates, like the CCX or Toffoli gate with 0 and 1 as control qubits and 2 as the target qubit. So once again, remember that pattern is that your first few numbers here are always going to be the control qubits, and then your remaining number will either be the target qubit. There's also a controlled swap gate. So the a controlled swap only needs 1 control qubit, but it's kind of special in that it has 2 targets. So in this case, I'm saying, or qubit 2 is the control, and then qubits 3 and 4 are our targets. And then I can still, as usual, just draw it out and get a very nice visualization of what exactly is going on here. Being able to extract the state vector, that pattern still holds, although now you'll notice the state vector looks gigantic because we have 5 qubits in total. So that's 2 to the power of 5 entries in the state vector. And the unitary matrix will be even bigger because it's 2 to the 5 by 2 to the 5. But the point I want to drive home though is that all of the syntax still holds, and it scales up very nicely. There's very little, if anything, you have to do to adapt for these larger states, other than a performance penalty, because eventually, once you start getting to like a higher number of qubits, you're definitely going to see performance degrade unless you start running this on a real quantum computer. And you should be able to visualize all the qubits here too. So once again, plot block multivector comes to the rescue, and it automatically decomposes the original vectors here. And state city still works as well, although you can tell that this is a bit of a mess because there's so many possible basis states to iterate over, because I've got 5 qubits here. So you can see these labels kind of crowd, and in this case, it doesn't make for a fantastic visualization. But it's still something to keep in the back of your mind that this still works for any number of qubits. Rules for simulation and measurement remain the same, so I can still use qc.measureAll to add the measurement gates, or the measurement operations, I should say, to all the qubits and store the results in the corresponding classical registers. So qubit 0 will go to classical register 0, qubit 1 goes to classical register 1, so on and so forth. And then I can still get the counts here, and we see that we're in 1 0 1 0 0. Although technically, once again, keep in mind the Qiskit ordering is reversed. And furthermore, custom initialization still holds, but in this case, I wanted to show off the fact like, hey, you can pass in a integer here, and then this integer will be automatically translated to binary, and that binary gets used to give some kind of initial state for your quantum circuit. And just to be on the safe side, we can certainly check by passing in the quantum circuit with this single initialization to the state vector tool here, and that'll give us the state vector after going from ket 0 and then being initialized. Custom gates still hold, but in this case, there are, I think, 2 more features here. So in terms of custom controlled gates, we can do some even crazier stuff. So one of the examples here that I've set up is that let's say we want a controlled X gate that only applies when the control qubits have the state 0 0 1 1. So in this case, I want a control gate that only triggers on a very specific state, on a single state. So in this case, we can just piggyback off of the fact that Qiskit already has X gate and build up from it. So what I mean here is like from the circuit library that I used in the very beginning, we can get the X gate, and X gate is, or the vast majority of them support this dot control method. In this case, notice my arguments here. So I'm saying I want 4 qubits for the control. I want the control state to be 0 0 1 1, and I give this fun little label. It's a crazy controlled X gate, and we have a quantum circuit with 5 qubits, and I'm going to append it because Qiskit definitely doesn't just naturally support a gate that only triggers on the state 0 0 1 1. And for this custom controlled X, notice that the first qubits here, so 0 1 2 and 3, are my control qubits, and then 4 is going to be my target qubit. And we can even see from the coloring here, which is kind of a nice hint, is qubit 0 and qubit 1 have to both be 1, and then qubit 2 and qubit 3 both have to be 0 for this qubit to get triggered. We can go ahead and test the circuit. So we expect that for any other initialized state, nothing should happen, and the initialized state stays as is. So in this case, I'm going to initialize to the ket 0, although in fact, this is probably redundant because all circuits automatically start in ket 0. Go ahead and hit append, and then I'm going to get the state vector. And you notice that despite the fact that this has so many entries, we can tell, in binary, right, this would be ket 0. So cool, nothing's changed here. And we can even visualize it, right? So plot block multivector. So all of my control qubits were in 0, so then nothing should happen to the 4th qubit here. But if we set the initial state right, then the gate gets applied. So I'm going to rebuild the circuit with my 5 qubits. Now the initialization here, so even though I said it would trigger on 0 0 1 1, I have to add this other 0 because we do have the target qubit. But another option you could have had here was to just say 0 0 1 1, and then I think you'd pass in another argument here saying like only apply these integers to like this subset of the circuit, and then you can leave one of the qubits alone. Although I felt this was a little easier and cleaner to think of mentally. So I'm still going to apply it with the same arguments where 0 to 3, the qubits 0 to 3 are my controlled qubits, and 4 is my target qubit. And we can go ahead and take a look here. And now we'll notice that we are, the 1 isn't here, and it's over. So off the top of my head, I think This is the right state vector. But if we're ever in doubt, because this isn't, we're not doing any entanglement, we can still use the plot block multivector. And we notice, voila, qubit 4, which is the target qubit, is now in ket 1 instead of ket 0. And you can see like all these other qubits here have been changed. So remember, I passed in that string 0011, but you know, you read it the other way around, because now qubit 0 is 1100. So just another reminder that Qiskit does flip the ordering here. Another thing that's really nice is that Qiskit allows you to create gates from entire circuits. So sometimes you know, you'll find when you're building a custom gate, it may be easier not to just like, you know, go into NumPy and build this unitary matrix from scratch, but rather to make a smaller circuit, put in all the gates you want, and then use that smaller circuit as kind of a subroutine. It's almost like when you write a traditional program in computer science, and you'll break it up into a bunch of smaller functions to make it more maintainable and easier to work with. And in fact, one of the demonstrations I have slated for you guys is it will use this functionality. So this is slightly modified from one of the existing things on the Qiskit documentation. But basically, let's declare our quantum circuit here. And notice I pass in 2 because it's only going to have 2 qubits, but then I can pass in a name as well. In this case, the name is sub-circ, for like a sub-circuit. And then on this sub-circuit, I'm going to apply the Hadamard 0. And then we also have sub-circuit CRZ. So this is a controlled Z rotation. So it's a 2-qubit gate, but it's a 2-qubit gate that accepts a parameter. So theta, which is the amount of rotation, I've set that to 1. And then these last 2 numbers here, you know, has a control qubit 0 and a target qubit being 1. Now, there's also something called a barrier that comes up in a lot of Qiskit textbook demonstrations, and it serves basically 2 purposes. The first purpose is it's a nice visual. So it's a way of saying like, oh, maybe this part of the circuit is like the first step, and then this second step is to remain separate from the other steps, in which case we can use a barrier as a nice visual indicator. But it has an even more important role when you're transpiling your circuit. So most of the times, you know, when you've built a circuit and you want to run it on an actual quantum computer, and you're sensitive about performance, what eventually happens is usually your circuit may have gates that aren't natively supported by hardware, or maybe, you know, and you also want to make sure that the quantum circuit has the least number of gates possible, because we know that qubits are very finicky and unstable things, and you know, over time, you know, error creeps in, and so it's ideal to keep the number of gates as small as possible. So there's a number of optimizations that Qiskit automatically can do for you, or you can explicitly call yourself to decompose the gates and to kind of minimize the number. If you apply a barrier to your circuit, what you are effectively telling this optimizer, or the transpilation process here, and transpilation is the name, by the way, of the process of mapping from maybe your custom gates to the gates that a certain hardware platform can support. When these processes are going on, and it encounters a barrier, basically it says like, look, it's going to treat each side of the barrier as a separate optimization process. So it could be possible in my optimization that this RZ and that and this gate here and this identity here could be combined together somehow. But because I have this barrier here, it's going to stop the optimization before the barrier, and treat like this part of the circuit entirely independently of the other part. So you will definitely lose out on certain optimizations, but it might be nice if maybe you're doing research and you don't want it to be optimized, or for visual purposes, you just want to split your circuit in 2 and emphasize the fact that this next part of the circuit is independent of the other part. So that's what a barrier is. And then you see I apply an identity gate onto the second qubit here. And there's also something called a U gate here. And the U gate takes several parameters, and it allows you to denote an arbitrary rotation on your on the block sphere. So this kind of allows you to rotate in any direction you could ever think of. So in this case, the first 3 numbers here are the amount of rotation on each respective axis, and then you would have 0 here, which is the index for the qubit we want to apply it towards. And we can go ahead and draw it as well to visualize it. Now, to use this sub-circuit as part of a bigger circuit, what we do is we convert it to 2 instruction. And once again, this harkens back to the fact that I mentioned that these quantum circuits are actually sequences of instruction objects. So what happens is we're going to decompose our circuit or sub-circuit into this list of instructions, and then we can inject that list of instructions into an even bigger circuit. So now, in this case, I have a 3-qubit circuit. I'm going to just do some arbitrary setup here by applying Hadamards and CX gates, and then I can append this sort of a sub-circuit. In this case, I call it sub_inst because now it's just a list of sub-instructions, and I apply it to qubits 1 and 2 here. And lo and behold, it comes out very nicely. So one note that I want to give you is that if you simulate the circuit off the bat, sometimes you'll run into an error that might say that sub-circuit isn't recognized. So, and in a full execution pipeline, a lot of the gates you see are decomposed into another gate set that the hardware or backend like natively supports. So, for example, a TOEFL, if it doesn't have like a native implementation, is actually just a bunch of CNOTs. I think it's 6, along with a bunch of intermediate single qubit gates. And when you run into such errors, fret not. Usually all you have to do is punch like .decompose, or not punch, but add a call to .decompose on your sub-circuit here, and then convert it to instructions, and it should be happy, because that .decompose breaks it down into like the individual gates instead of keeping it as a coherent sub-circuit. And I'll give an example of what that might look like in the Grover's algorithm example coming up here. All right, so now hopefully we've covered a lot of ground with what Qiskit can do, and now I bet you're probably itching to see, what exactly, like, what's the culmination of all you've learned. So hopefully these 2 examples here will be exciting enough for you. And my first example here is Grover's algorithm. So I've been told you already know this algorithm, so I won't spend too much time on the mechanics and focus more on the code here. So one of the things I neglected to mention at the very beginning is that you can label qubits too, and this might be nice to kind of make it easier to keep track of your qubits. So what you can do is you explicitly declare your quantum and classical registers as separate entities, and then you can initialize a quantum circuit with them, although a quantum circuit with just the 2 integer arguments will do just fine as well if you don't care much for register labeling. So in this case, I'm just importing not just quantum circuit, but also this classical register and quantum register class. And basically what I'm saying here is, well, look, for Grover's algorithm, you have an oracle function, and basically that function is designed such that it recognizes a right answer. So in this case, for our function input qubits, I create a quantum register with, in this case, 3 qubits, and I label it X. And then we have a target qubit, or the quantum register. It's also a quantum register, which only has 1 qubit, and then I label it f of x. So the idea being, in Grover's algorithm, there's going to be 1 target qubit, and if any of the entries are correct in the initial states that I feed this function, it's going to do phase kickback, and then we can amplify. We can use that kickback phase to amplify the right answer. So what we're going to do here is we store our results here in the classical register, and then we're going to go ahead and create a quantum circuit here. So once again, we just pass in the classical registers along with our 2 quantum registers. So now that we have this initial circuit set up, we can set up what I call the initialization phase. So we know that all of the input qubits have to be in a superposition state. So we just apply a bunch of Hadamards across the board on the function inputs here, so x0 to x2. But the last qubit should be in the kickback position. So in this case, it's ket minus essentially. So we'll put an X gate first on the 3rd qubit here, or qubit 3, and then we'll apply the Hadamard to it to go from ket 1 to ket minus. And then we can draw it and get a nice visualization here. And you'll notice that with the custom labels, they also get rendered very nicely, and we can kind of it gives us a better way of handling multiple qubits in larger circuits. And we can still, right now there's no entanglement going on, so we can visualize the current state after execution using the same methods here. But this time I've shortcutted things, so I am not saving the state vector to a separate variable. I just feed it directly into the plot block multivector, and this should make sense, right? Because qubits 0 to 0, 1, and 2 are all in the ket plus state, where they're pointed in the right on the X here, and then qubit 3 here is ket minus. So it's flipped the other way around along along the axis. Now I'm going to go ahead and apply a barrier here. And this is just a symbolic meaning to denote, like, look, the initialization phase is done. And in this case, we're going to create an oracle. And the oracle is going to recognize the answer to x0 and x1 and x2. So it's a Boolean statement here. And any configuration of bits that satisfies this will induce the phase kickback that we need. So it applies a negative. It'll induce the phase kickback here. And one of the things I want to mention is that, so note that when the circuit actually gets run on hardware, the gate actually gets broken down into smaller gates. So in this case, CCX, the CCX might get broken down into CX and other single qubit gates that are native to the hardware, because the hardware may not support a CCX natively, in which case there's a certain subset of gates that are universally, that the hardware does support. And then you'll have to do something like transpilation, something I mentioned earlier, that'll automatically break it down for you. And the inspiration from this oracle comes from CNOT.io, which is another fantastic resource, as well as Ryan LaRose's quick seminar notes on Grover's algorithm. And I should have mentioned this earlier, but hats off to Ali Javadi for giving some the register naming code here. And this is also based off, I should have mentioned this earlier as well too. This Grover's algorithm implementation is based off a lesson that I gave at Quantum Computing at Davis, and which you're more than welcome to refer to and check out if you want to learn more about Grover's algorithm, or imagine for Clarice's class to refresh what you already know. So in this case, one of the gates that can represent, one of the gates that can perform this oracle behavior is the multi-controlled X gate. .mcx, and in this case, I'm saying that 0, 1, and 2 are the control qubits, and then 3 is my target qubit. And then I could go ahead and draw it here, and you can see that this MCX gate is the oracle. And if you think about it, it does represent this behavior, x0 and x1 and x2, because if you plug in, the only state this will work is if all of these are ones, right? So with an MCX gate, if I plug in 1, 1, and 1, then it'll actually apply the X here, in which case then it'll have the, it'll induce the phase kickback. So with the oracle complete, I'll put another barrier down just to denote that this is a distinct part of the circuit. So just for visual purposes, and then we can just draw it and see it here. Now I've taken, now we're going to implement Grover's operator. So this does the heavy lifting in the circuit. It's going to do inversion about the mean. And because we've flipped the probability amplitude associated with the correct answer, it's going to, it'll have the effect of amplifying the amplitude of the correct answer while reducing the amplitudes of the incorrect answers. So in this case, basically just apply all these Hadamards, and we still have another multi-controlled X gate. And these only, this operator will only have to work on x0 to x2, so the first original 3 input qubits here. So now that we have the circuit set up, we want to probably get results here, and you probably want to use measure all, but that actually fails here. And the reason being is that we don't want to measure the f of x. We actually don't care about it, because f of x, the f of x qubit is only there to help with the phase kickback. What we actually want to measure are the 3 qubits up here. And the way we do that is we just use measure instead of measure all. And we're going to say, like, hey, take qubits 0, 1, and 2, and then map them to classical registers 0, 1, and 2. And you can see I already anticipated this because there are only 3 classical registers, which is exactly what we need. I still use the same syntax for the state vector simulator, and then we can go ahead and hit backend.run, and we create the backend, run it, get the results from the job, and show the counts via the plot histogram function. And we'll notice the correct answer here is, has a significantly higher chance of being measured than the other states here will have diminished probabilities of being measured because they don't satisfy what the oracle is looking for. Now, what if we want to apply Grover's operator one more time? We know that successive applications of Grover's operator up to a point can amplify the amplitude of the correct answer. But the problem with that, something else to keep in mind is if you apply it too many times, you end up overshooting. So you actually undo the work that you do, because you have to remember with Grover's algorithm, it does the inversion about the mean, right? So if we start in this initial state, so this is where our average is, And then, we do the phase kickback. So in this example in the slides that I've made for that Grover's algorithm workshop, the mean is reduced. And then in this case, we get the right answer. So now the mean is reduced even further. So if I were to apply it again, well, then it's going to do the inversion about the mean. And essentially we just revert back. Then we're just back to the original answer, the original equal superposition, which isn't helpful to us. Just an aside here. But let's see, will that actually happen to this circuit? But first things first, let's actually tidy things up. We know in any application of Grover's algorithm, we'll always have an oracle and we'll always have the Grover or diffusion operator. I personally like to call it Grover's operator, although I know it's also called the diffusion operator after some roots in, I think, a fluid dynamics problem, if I'm not mistaken. But don't take my word for that. I'd encourage you to double check that yourself. So to make it easier to repeatedly apply these, the oracle and the Grover's operator versus having to copy and paste all of this code and over and over, why don't we take advantage of what we've learned with developing sub-circuits as gates and custom gates and apply that moving forward. So in this case, I'm going to get the MCX gate. So it's the same thing that you saw earlier for creating the oracle, the multi-controlled X gate. And in this case, I'm going to say, it's still the same thing here, but with more explicit arguments. So the number of control qubits is still 3. But this time I'll label it explicitly as an oracle, and the control state should be 111. And now I save it with this variable oracle. And then I can, for the Grover's operator, remember it only applies to 3 qubits out of that 4-qubit circuit. So the easiest way to go about this, because it's multiple gates versus 1 gate, is to create a subcircuit with the following name, Grover's operator. I apply all the gates that I want, and then I go ahead and rebuild the circuit. So we're still using the same register labelings or qubit labelings as last time. I still have my initialization phase going on here, but then the barriers here. But now notice that I have 2 append instructions here. One for the oracle I defined earlier. The control qubits are still 0, 1, and 2, and then we set the target qubit to be 3. And then for the operator here, I just do this. I just apply the circuit and I say hey, apply that circuit to qubits 0, 1, and 2. Now you'll notice I have to invoke .decompose here. And what that means is, internally, I've just told it to use the underlying gates that were made up in that circuit, because if you try and run it without decomposing it on the simulator, it's going to yell at you. But in this case, this looks much nicer. And notice it only took me, several lines versus, maybe many multiple lines to perform this operation. So now that we've kind of bundled everything together, we can apply the same things again, just by repeating ourselves here. And lo and behold, now we have 2 applications of the oracle and 2 applications of Grover's operator. So now let's see how the results hold up. This is the same thing you saw earlier. So I'm basically telling it to measure qubits 0, 1, and 2 and save those results to classical register 0, 1, and 2 using the, we're going to use the state vector simulator, and then we're going to run it 1,024 times, and then we get the counts. Once again, the counts being the number of times you measure any of the basis states from 0, 0, 0 to 1, 1, 1 in our case, and we plot the histogram. And this looks even better, right? Because now it's 0.954 probability of measuring 1, 1, 1, which is the right answer, versus and then all the other wrong answers have an even smaller chance of being measured. And once again, our circuit, the circuit with the measurements looks like this. So just to reiterate, we can't use measure all here because we don't want to measure f of x. This other qubit here is just sitting around for the phase kickback step. So we have to use qc.measure like this, where you say look, from quantum bits 0, 1, and 2, go to the classical bits or classical registers 0, 1, and 2. All right, so now you know how to simulate Grover's algorithm using Qiskit. But there's another thing I want to show you called a Givens rotation. And this is partially working. And this is sort of, not just to, I'm having a little joke here, a fantastic way to turn my hasty work into a learning experience for you guys, but more rather, it's a nice way to show you guys what I encounter in my job as a quantum software engineer. And it's kind of an exercise of debugging quantum circuits. So what exactly is a Givens rotation? So here's the explicit definition for Penny Lane, and it's a rotation in a 2-dimensional subspace of a larger Hilbert space. So in the example here, so in this case, we are performing a given rotation in a two-dimensional subspace of the four-dimensional space of two qubit states. So just to give it a visualization here, if you imagine you have two qubits, right? That gives you four possible basis states, right? So from ket 0, 0 to ket 1, 1. And you can kind of think of those as creating a vector space, right? And there are times where you want to perform a rotation around two of those vectors. So the two-dimensional subspace. And why exactly is a given rotation useful at all? Well, it comes up a lot in quantum chemistry when you want to simulate. In this case, the example that Penny Lane gives is you have a single excitation. I'm getting ahead of myself here. It's it's part of a particle conserving unitary. So if you're simulating like these electron states on the quantum computer, and you want to be able to represent the excitation of an electron, but at the same time, you want to preserve the number of electrons, right? You don't want some unitary that just throws in an electron or a unitary that removes an electron. So I think the other name that I guess the Penny Lane people have called it is a particle conserving unitary. And this will come up, you can use these given rotations in things like VQE, the variational quantum eigensolver, where you're trying to find the ground state of some multi-electron molecular configuration. So in this case, we're not just implementing any Gibbons rotation, because I'm pretty sure other frameworks just have the Gibbons rotation for you, but rather there's something as part of my work with quantum computing at Davis is we wanted to be able to run this Gibbons rotation on an IonQ machine, IonQ. So it's an ion trapped architecture. And you remember earlier I mentioned, albeit not as explicitly, but I did mention that different quantum computers support different sets of native gates. So in this case, the IonQ quantum computer supports a different set of basis gates than, say, the IBM Q superconducting gates. So this was basically an attempt to develop this here. In fact, let me show you what the original paper looks like. If we take a look here, this is the paper from Google. So this is the circuit that represents the Gibbons rotations. This is a paper by Google, Hartree-Fock on a superconducting qubit quantum computer, written by the Google AI quantum team and collaborators. And the idea here is that this circuit here, this thing here with the square root I swap and then the minus theta, theta plus pi, another square root I swap and then pi, this is what we want to build for our ion trapped computer. And you notice that each theta is really an RZ gate. So this is what I meant way back earlier when I showed you the rotation gates with Rx, Ry, and Rz. You're really just putting in that Z, X, or Y as the exponent of this, e to the X, but with a theta too. So the theta will allow you to define a certain custom amount of rotation. So we're going to try and implement this circuit in Qiskit. And this circuit was designed originally to, I think, run on Google's computers, but for my team's work, we want it to run on the IonQ quantum computer for quantum computing at Davis. So let me go ahead and hit new share. Let me go back to the notebook here. So the first thing is that it has a square root I swap gate. So let me explain what that is. A swap gate, as you know, the classic identity is just 3 CX gates that are kind of alternated. But the swap gate just goes ahead and swaps to qubit states, and that's allowed, right? We can't copy states, but we can certainly swap them. The I swap, if I remember correctly, is that once it does a swap, it adds an imaginary phase, like a phase of I think, to one of the qubits, and then the square root of that is like going halfway through that. I know that's a bit lazy, but another intuitive way to think of this is I know some of the, I think S or T can be thought of as the square root of another gate, and intuitively that means you're going halfway versus the entirety of that the original gate that you square rooted. So in this case, I'm going to represent the square root I swap by using that trick I showed earlier. We take the quantum circuit. It only takes 2 qubits, and then I go ahead and apply all my gates here. And I should mention the code here was actually based off something I wrote myself, but using Google Circ. So I'm also porting this code from Circ. And you notice that Circ is a very, it may not be as beginner friendly in my opinion, but it's certainly still robust. And I think it might cover a separate domains than Qiskit does. But yeah, so I'm porting some existing work here as a demonstration in Qiskit for this Gibbons rotation on an ion-trapped computer or ion-trapped quantum computer. So I've given it the name skirt ISWAP. We apply all of our gates here, and you notice that this is kind of nice about Qiskit too. The Z gate, right? So remember I said it was an R, so it was a Z gate with a certain degree of rotation, and that's the equivalent of putting the Z gate or the Z matrix itself as part of the exponent. Well, it even Qiskit offers this dot power method that does that operation. You can plug in the theta value that you were interested in putting into that exponent that gets multiplied with the Z matrix in the e to the x. And basically, I'm saying like I want you to raise it to the 0.25 power, and then we'll apply it to the first qubit here, and we have our full-blown circuit here. Now, to create the full actual Gibbons rotation, besides having the skirt ISWAP subcomponent, also notice that in that diagram I showed you from the Google paper, there were a bunch of RZ gates, and you were able, and they had theta as an argument. So theta is a value that you will plug in externally. And one of the ways you can create what we call like these parametrized circuits is in Qiskit, you can define a parameter, literally a parameter object, and then you'll give it. So this string is the name of that parameter. So when I print it, you'll notice it says like theta here, theta plus pi, and the negative 1.0 times theta. But in reality, the actual name that you as a developer will address is the English rendition here that's the variable name. And you'll notice that for RZ, instead of putting a number here, I just put in this theta parameter object. And what happens is when I want to actually use it, or I want to actually use the circuit here, I can bind the parameter. I bind it. But I've jumped ahead a couple steps, so let's visualize what we see here. So notice the skirt ISWAP are both here as subcircuits, and then the RZ gates are interspersed. This should look exactly like what that Google paper showed us. And just to see what parameters my circuit takes, I can just use the parameters attribute, and this gives me a parameter view. For the full simulation, what I can do, I'll just to really see if it works or not, I'm going to initialize the circuit to be a full even superposition, which is also the equivalent of applying 2 Hadamards. So I just make this list here where every entry is 1 over np dot square root of 4 times 4. So this syntax is like Python shorthand to say like repeat the entries of this list 4 times. And then we can go ahead and initialize it using this list here. So this targets both of the qubits, and then I'm going to append my custom circuit here. And note that once again, I'm using this bind underscore parameters. So theta was the name of the parameter object that I created, and I'm going to say like, look, I want to assign the value of np.pi over 3 to theta, and then I have to call this, and then I call dot to underscore instruction to turn this subcircuit into a list of instructions that get injected into my main circuit, keeping in mind that this subcircuit should target qubits 0 and 1. So if we draw it again, lo and behold, we have our initialization component, and then we have the Gibbons rotations here, or the given rotation is provided here. So this is close. So if we look at the results here, I can basically get the results by just using state vector again. These statements here just get you the raw NumPy array from the state vector. But then I do this reshape. So reshape is a NumPy inherent method. And the idea is you can pass in a NumPy array, and then reshape says like, look, I want you to convert this array to have 4 rows and 1 column. And the reason why I do this is because this format, 4 rows and 1 column, is much easier to work with for matrix multiplication, because by default, I think the NumPy arrays come out to be 1-dimensional when represented as a state vector. Yeah, reshaping it to 4 rows and 1 column makes it much friendlier to do matrix multiplication on with a raw NumPy matrix. And then I'm saying we'll round it to 3 places using np.round. Let's say I want to finally get the, just to continue my probing of this circuit, I want to get the unitary matrix that represents the circuit. The problem is if you have a measurement gate, or I think even with a custom initialization, you can't really do that method I showed you last time, which is just using the operator, creating an operator object, and then feeding in the quantum circuit and then getting the unitary by using the .data attribute. Instead, what you can do is you can create a unitary simulator, and then and make sure that the circuit doesn't have any measurements, and then pass in the quantum circuit into the unitary simulator, and then you get the result out. And this should be the unitary matrix of your circuit. From the result, you just do .get unitary, feeding in the quantum circuit again, and then also mentioning, like, look, I only want this many decimal places, and we get the unitary matrix that represents our given insertion. Now, something I can already tell as the quantum software engineer that something is not right here, because this is the matrix from the correct implementation. So the correct implementation being this guy here that I already implemented in Google Circ, and we'll notice that yeah, some of the entries seem to have the wrong phase, but the bigger issue here is that there are a bunch of like negative 0.5s where there shouldn't be any at all. And to really sort of drive the point home, now that I have the correct unitary matrix here as a raw NumPy array, I can do that thing again, where I can represent the state vector in NumPy. So I create the state vector in NumPy instead of using Qiskit. In this case, this is an equal superposition, and then I reshape it to have 4 rows in 1 column. And then the @ here is how you would do a matrix multiplication. So saying like yeah, it's how you would do a matrix multiplication in NumPy itself, and then we get our new state vector. So the reason for doing this kind of thing is there are many times where you know, as I'm emphasizing in the very beginning, right, is as an engineer, you may want to be able to really look at the raw underlying math and make sure that what you're developing is behaving the way you want it to. So in this case, I'm lucky in that I have a reference and I can consult whether or not the circuit agrees with the reference implementation, in which case it doesn't. So I know that, okay, there's something wrong with maybe the way I've implemented my circuit, and I may need to backtrack here. And then, you know, being able to quickly, you know, off the top of your head, create custom state vectors using NumPy and then multiplying against raw matrices are a fantastic way to really get some fast debugging done when you don't want to deal with maybe the overhead or the abstraction that any quantum computing framework provides. So with that being said, those are the 2 applications that I had for you. I want to say thank you very much for watching this video, and hopefully you've learned a great deal about Qiskit. If you have never touched Qiskit before, I certainly hope you're encouraged to use it as maybe as your first quantum computing framework. And if you already maybe a Qiskit pro or a huge Qiskit enthusiast, then I hope you might have learned a thing or two you weren't aware of before. And well, you know, if you haven't learned anything new, well, at the very least, now you kind of know maybe my debugging process as a quantum software engineer. This idea of being able to comfortably go back and forth between raw unitary matrices and state vectors in NumPy to Qiskit objects or really objects in any quantum computing framework. So thank you so much. And to all of Clarice's students, I hope you know, this will prove valuable in your future projects and in your careers even in the quantum computing space. Thank you so much for your time, and hopefully I'll be able to see you in another lesson. Thank you very much.